So when I say we are finding arc length, to kind of be clear, when we talk about arc length, I did want to define that for us. So when you first learned that phrase, or really that word arc length was defined as basically a part of a circle. And kind of like how we've seen in calculus, like different words we used in geometry with circles are kind of expanded into calculus terms. For example, when you first learn the terms tangent line and secant line, those are referring to lines of a circle. And then we expanded and said, hey, actually a tangent could be any line, tangent to a curve, not just a circle. Graphs also have secant lines. Same thing's going to be true for arc length. So like arc length, yes, is part of a circle, but technically arc length could be any part of a curve. And so what we're going to be focusing on today is how we actually find the length of a curve. This shows up in different ways in calculus, like sometimes you are just asked to find the length of the curve. It can also be used though to find things like the perimeter of kind of these shapes defined by one or more functions. I could just give you the formula. I think this one is nice to kind of see where the formula comes from. It will help you kind of remember it. I think it also just is kind of a neat formula to see where it comes from. But when we're talking about arc length, I think it's best to kind of start off by talking about like where we can even approximate arc length from. So like here's this function. If I want to find the length of that blue section, like it's not like I can get like a tape measure and just like measure how long it is. Like you want to use the math to figure out how long that arc is. And the easiest way to approximate the length of that arc is kind of like, think back to your Riemann sums. Like we use rectangles to originally approximate area. Well, if I want to approximate the arc length, you just kind of think about like, if I connected a line between those two, that should be a straight line, but if I connect a line between those two, like that would be a good approximation of that curve. How could I find the length of that line? I could kind of think about a right triangle, because those are going to be a lot easier to deal with than curves. How can I use a right triangle to approximate the length of that curve? So again, I'm going to say that this L is approximately the same as the arc length. We often use a lowercase cursive L for arc length. Well, if I want to find that L, I can kind of think about the Pythagorean theorem. That horizontal side is like delta x is the change in the x values, and the height of it is kind of like the change in the y value. So like ultimately we're going to think about how we can convert this to a calculus formula where that arc length is approximately given by the Pythagorean theorem of like L squared is equal to delta x squared plus delta y squared, and then like take the square root of it. Well, how can we convert this into a calculus formula? Right now, this is just like your good old Pythagorean theorem. Also not the exact arc length, that is just an approximate. Where we can kind of get the calculus formula to come from is, imagine to yourself, like you really want to approximate the curve, just choose like smaller and smaller triangles. Like the smaller the triangles, the closer it's going to fit. And ultimately, when it comes to calculus, you want to think about adding up like an infinite number of little right triangles. Again, those are right triangles, but trying to find all those hypotenuses, adding them together, and that will give you what that arc length is. Well, how do we represent those itty bitty bitty tiny triangles? Instead of writing delta x, we want just like an itty bitty change in x. So in calculus notation, we want to think of this as dx. Same thing for y. If we want to think about an itty bitty tiny right triangle, we'll think of delta y as dy. And that's going to be the basic idea that we're going to use to develop this calculus formula. It's going to be like another integral formula that we use. And so there are going to be two formulas that we're going to think about when we're using this defined arc length. So I'm just going to kind of focus on the right triangle part. Again, we're going to use L as like our approximation for arc length, dx for the change in the x value, and dy for a change in the y value. And the way that we're going to convert the Pythagorean theorem into a calculus formula is we are going to have two of them. We know just like with area and volume, sometimes we do it in terms of dx, sometimes we do it in terms of dy. And to turn this into a usable calculus formula, you're either going to divide every side you see by dx, or you're going to divide every side you see by dy. And what I mean by that, like if I go ahead and divide everything by dx first, what we end up getting, I'm going to slide this up a little bit. Is, there we go. Dividing everything by dx, we're going to have like L over dx. The dx becomes dx over dx, which is 1. You can kind of imagine doing calculus, dealing with 1 is going to be easier. And then this other side, we have dy. Well, dy divided by dx becomes dy dx. So you can kind of see where the calculus is coming into play with this one. Or the other way to come up with the formula is you divide everything by dy. Dividing everything by dy, we have like L over dy. We have dy over dy, which is just 1. Or we have dx over dy, which is a derivative, but it's the derivative of x with respect to y. Why are we doing this? What is this going to eventually become? It is going to become the rules that we're going to use to find the length of an actual arc. And where the formula comes from is it is basically the Pythagorean theorem. So when we're approximating this arc length, so I'm going to have one side squared plus the other side squared. If I'm solving for L, this was L over dx, but I'm going to go ahead and it is L over dx squared. But I'm going to like take the square root of both sides, so I have what L is equal to. L was divided by dx. Since I am just kind of finding an arc length, I'm going to take the dx that L was divided by and kind of move it to the other side. That would be representing one triangle. Well, if I want to represent an entire arc length, we want to add up a whole bunch of infinitely tiny triangles. How do we show the sum of a bunch of infinitely tiny rectangles? We're just going to take the integral of that expression. So that is basically going to be your first formula, but we're going to call that, again, arc length is equal to the integral, we'll say from a to b, of the square root. Dx over dx is just 1. 1 squared is just 1. Plus, we have dy over dx squared with respect to dx. So that's going to be the first formula that you can kind of learn and use and memorize. We can do a similar thing with the other triangle. So again, L would be equal to the square root of, I have the dy over dy, which again is just 1, squared, plus dx over dy squared. Took the square root, moved the dy over to the other side. How do we find the arc length? We take the integral, because we're going to add up a bunch of little triangles. Dy over dy is 1, 1 squared is 1, plus the derivative of x with respect to y squared dy. Why do I show you that? Like many of you probably would just be fine if I said, hey, here's the formula for arc length and memorize it. But I think when I just showed you that formula, you see at the very bottom, like you lose the context that this really is just like a fancy version of the Pythagorean theorem. And that's really what we're doing. We're just taking something that we already know. We know how to do the Pythagorean theorem. We're just kind of changing it. So now that's going to be like this integral. Doesn't look like the Pythagorean theorem anymore, but really it is. I'm going to rewrite those formulas just on the next slide, and then I'll kind of take questions on them before the examples. So again, we do have two formulas to use. Doesn't matter in this case which one you choose. So like when you do area and volume, you often decide like, hey, is this a dx problem or is this a dy problem? For arc length, you just pick whichever one you think is going to be easier. With respect to x, the arc length is going to be given by the integral from a to b on the square root of 1 plus the derivative of y with respect to x squared, and we're doing this with respect to dx. The bottom part of the derivative will always match what you're doing it with respect to. That's kind of how you know you set it up correctly. If you're doing this in terms of dy, still from a to b plus the square root of 1 plus. If you're doing it in terms of dy, you have dx over dy squared. And again, what matches? Dy and dy. For both of them, A is always going to be less than B, so those numbers will always go in order. So either it's going to be like left to right or like bottom to top. And they both give you the same answer. So you basically choose which one you want to do. I will say don't always think that with respect to X is going to be easier. Sometimes, especially if you're evaluating it by hand, that doing it with respect to Y actually simplifies a little bit nicer, and that's the one that we're going to choose. But those are the two formulas that we have. Questions on those formulas before we start looking at some examples. All right, so let's go ahead and look at the first example. These are pretty straightforward, especially if we're not going to evaluate it. I will say a lot of these, if you are asked to evaluate it, you either have to use the calculator because of the way the integral looks, you just can't do them by hand. Or, unfortunately, if you are asked to evaluate by hand, it's usually like a whole lot of algebra to simplify it, and then you're able to find the antiderivative. So let's talk about this one. We want to find the length of the function y is equal to x squared. So we actually want to find the actual length of that curve that we would sketch from x is equal to 1 to x is equal to 4. So if I just kind of draw what that graph looks like, and again, we're just going from 1 to 4. I know this is my basic quadratic, and we want to find the length from 1 to 4. So that part that I have highlighted is what we want to find the length of. Like, it's not a straight line, so you can just like measure it. We are going to kind of use calculus to find the length of it. I'm going to do it in terms of dx because right now all those terms are in terms of x. So I know that the arc length of it, so I'm just going to write the formula again. If I'm doing it in terms of dx, we have 1 plus dy dx squared. And it really is this kind of basic to kind of set up. What is the length of that arc? Well, if I'm doing it in terms of x, we're going from 1 to 4 on the square root of 1 plus the derivative of y with respect to x squared. Well, if y is x squared, dy dx, which is again just the derivative, would be 2x. So I just plug that in, and there's my arc length. This is one that we couldn't evaluate by hand because that inside is going to become like 1 plus 4x squared. So there's going to be no like u sub on the outside. So that will be either a setup or a setup and then evaluate in the calculator. Questions on that? All right, try that same problem. So same graph, but try it yourself, but in terms of y. And I already did kind of the work for you, like wouldn't have to regraph it. But it's that same quadratic, but instead of going from 1 to 4 on the x values, I'm going from 1 to 16 on the y. It would give you the same answer, and especially if we were using our calculator to evaluate it, it wouldn't matter which way you did it. You would get the same answer, just kind of up to you, like which way is easier or how is the information provided to you. There's my answer. Again, it really is this straightforward. If I want to find the length of the curve, again, we have like our fancy Pythagorean theorem. If I'm doing it in terms of dy, it's going to be the square root of 1 plus dx dy, which means the derivative of x with respect to y. So you're taking the derivative of an x equals function. Well, y equals x squared is the same thing as y is equal to the square root of y. So taking the derivative of that, I get 1 over 2 root y. Plug it in, and again, it just told me to set it up. So that would be my answer. And again, what that represents, if I don't want us to lose meaning of that, that represents the actual length of the curve from 1 to 16. Questions? All right, let's do one that's a little bit more fun. Let's look at this one. So I have find the length of y is equal to the arc sine of e to the negative x. I wouldn't expect you to know what that graph looks like, but I have it there. And I want us to find the length of that curve from x is equal to 0 to x is equal to the natural log of 2. We are going to eventually do this in two ways. We're going to first do it in terms of dx, because everything has been given to us in terms of x values. Then we're going to go ahead back and do it in terms of y. On the next slide, what we're going to do is I want us to evaluate one of them by hand. So we'll have to make the decision of like, is it going to actually be easier to evaluate by hand in terms of dx? Or is it going to be easier to evaluate by hand in terms of dy? So let's go ahead and do the dx one first. If I want to find the length of this curve, and I'll just call that L, the length of this curve is the integral. If I'm starting in terms of dx, it's going from 0 to the natural log of 2 on the square root with respect to dx. I have 1 plus the derivative, again, dy dx. Well, there is my y. Y is the arc sine of e to the negative x. So what would be the derivative, y prime or dy dx? We just want to make sure we do our derivative rule correctly. This one will have kind of like a double chain rule in it. So again, what's the derivative of arc sine? It's 1 over the square root of 1 minus the inside squared. And then the chain rule times the derivative of the inside. Well, the derivative of e to the negative x is e to the negative x. The derivative of e to the u is just e to the u. Then looking at your exponent, negative x, what's the derivative of negative x? Negative 1. So that is your derivative, and we are just going to go ahead and plug that into dy dx squared. I'm going to simplify it as negative e to the negative x over the square root of 1 minus e. Squaring that means we're going to multiply e to the negative 2x. Who wants to try to evaluate that one by hand? Hopefully no one. I'm pretty sure you can't do that one by hand. But that is the arc length. Again, we just use the formula. And this is why sometimes we want to do something like, even though everything is given to us in terms of x's, if you had to evaluate this one by hand, this integral is not a friendly integral to deal with. Like, yes, you can square what's in there, but like the u sub isn't going to work out. Like it's just not going to work out. So sometimes you work it out, and you're like, well, maybe doing it in terms of dy is going to be a lot nicer. So we'll kind of talk about how we can convert it into dy. I chose this one also just because there is just like a lot of algebra that I think is good to review. So we're doing it in terms of dy. We do need to find the derivative of x in terms of y. I also need to make sure I put y values on my integral sign instead of x values. I'm going to go ahead and deal with the function part first. Let's talk about and remind ourselves how we can solve this one. So if I have y is equal to the arc sine of e to the negative x, let's solve this for x first. Well, if I have y is equal to the arc sine of e to the negative x, I can kind of flip that around. And that would be the same thing as saying the sine of y is equal to e to the negative x. Those mean the same thing. Again, I'm solving for x. What can I do to both sides to get rid of that e? ln. I can take the natural log of both sides. So this left-hand side becomes the natural log of the sine of y. And then the e will cancel out and just have negative x. So then solving for x, I get x is equal to the negative, go back and squeeze that in, the negative natural log of the sine of x. Sine of y, excuse me. So there's the x. Some students, I do see the mistake they make is like they do all that work and they think they're done, but remember we're plugging the derivative into that integral. So this is what x is. We still want to find dx dy. Well, now we want to take the derivative of this. So we have that negative there. Remember we're doing the derivative of a log function. The derivative of a log function is 1 over the inside times the derivative of the inside. So that's the chain rule. So looking at this, I see that dx dy is negative cosine over sine. If I want to simplify that, what is that just going to simplify to? Negative cotangent. All right, so the negative cosine over sine is the negative cotangent of y. Where does that go? That's going to go into where the derivative was and then squared. Questions on how I set up either of those integrals? We're not done with that dy one yet. Do need to make sure we can kind of put the numbers on there. So if we're looking at that dy integral, like we've plugged in the integrand, we still want to make sure we have numbers on it. Well, in terms of dx, that curve we were doing started at x is equal to 0 and ended at x was the natural log of 2. So if I want to figure out where the y values, where this is starting and ending at, I basically want to find the y of 0 and kind of plug that in, and then also the y of the natural log of 2. Plug it in and evaluate it. We're basically just finding the y coordinate that goes with those x coordinates. So again, what was the function we're dealing with? The arcsine of e to the negative x, so e to the negative 0. Well, e to the 0 is just 1. So I have the arcsine of 1. When is sine equal to 1? Pi over 2. Do be careful, just because that was what was 0 is, that doesn't mean that's going to be the first number on our integral sign. We still want to make sure it goes from like the smallest one to the larger one. So let's go ahead and plug in the arcsine of the natural log of 2. So I have the arcsine, the natural log of 2. So that's going to become e negative natural log of 2. Good review of some properties that you should know. I know that the e and the natural log will cancel each other out, but right now that negative is kind of in the way. That negative you can think of as a negative 1. Well, what can we do with coefficients in front of a logarithm? It can be moved up to become an exponent. So like if I move this negative 1 up as an exponent, that's going to become 2 to the negative first power. Well, 2 to the negative first power is just the same thing as 1/2. So then this is going to become the arcsine of e to the natural log of 1/2. Again, e and natural log will cancel out when they touch, so that's just going to become 1/2. When is arcsine of 1/2? That means when is sine equal to 1/2? Sine is equal to 1/2 at pi over 6 radians. So those are the two y values, and again, if I put this back on the graph, basically what this represents is when x is 0, the y value is pi over 2. When x is the natural log of 2, y is pi over 6. So then on my integral sign, where those go, always go from the lower one to the higher one. So we're going to be integrating this from pi over 6 to pi over 2. Again, took a while to get to that setup, but again, hope that kind of shows you the stuff we need to go through, and then also just kind of reviews some good like log rules and exponent rules and things like that. Questions on how I set that up though? All right, so the next slide, and I'll kind of show it, and then we'll go back to this one. We actually now want to go ahead and find that arc length by evaluating the easier integral without a calculator. So we took the time to set these both up. Which one are you most likely going to want to attempt to evaluate by hand? The with respect to y. Like they're both gross. Like let's get that out of the way. They're both kind of gross. We have like something squared inside of a square root sign, so we are going to be careful with like u sub or simplifying. In fact, if you're looking at this one, the only one that can be done by hand is the with respect to y. The with respect to x1 cannot be done by hand. So I'm going to kind of screenshot this and paste it on my next slide. And so this is what I'm basically going to try to evaluate. So let's talk about what we can do to evaluate it. Right now, probably don't want to jump into U sub, because again, there's like nothing really on the outside of that square root sign, so I want to find a way to simplify it. I do have this negative cotangent of y squared. Let's clean it up a little bit. When I square it, that negative is just going to go away. I'm also going to just ignore the numbers for now, just to kind of focus on finding the antiderivative. So we have 1 plus, this becomes cotangent squared of y, and with respect to dy. Still can't do u sub, because like if u was 1 plus cotangent squared, there's nothing on the outside of it. But does anyone notice if something can do with that problem?
1 plus cotangent squared y can be turned into, I think, cosecant?
Cosecant squared, yeah. So that's coming from your Pythagorean identity. 1 plus cotangent squared is not x, though. Let me be better about that. Y. And that's really what you're going to want to happen for a lot of these when you're doing algebraic. You want to somehow simplify it to some sort of perfect square, whether it's a trig one, whether it's an algebraic one. Because what makes these hard to do by hand is that square root sign. So now that that's a square, this is really just integrating the cosecant of y dy, which we can do because that is a rule we learned back in Unit 6. What's the integral of cosecant? The integral of cosecant is the negative natural log of the absolute value of cosecant plus cotangent. And then this was a definite one, so we're evaluating this still from pi over 6 to pi over 2. Then we can finish it out. We got done with the hard part, plugging the top minus plugging in the bottom. So I have negative natural log of the absolute value. Cosecant of pi over 2, I think the sine of pi over 2 is 1, so cosecant of pi over 2 is also 1, plus cotangent of pi over 2, that's going to be 0 over 1, so 0, minus the negative natural log of the absolute value, the cosecant of pi over 6, so I'm like, well, what's the sine of pi over 6? 1/2, so cosecant would be 2. And then what's the cotangent of pi over 6? That's going to be the cosine over the sine, which is just the square root of 3. I'm fine if you leave your answer like that, but that first term is going to become the natural log of 1. And we know the natural log of 1 is just 0. So the length of this curve is that value. The natural log, could have dropped the absolute value since that was going to be positive, but the natural log of 2 plus 3. Which you probably don't think is cool, but I think it's cool. Like if you imagine a tape measure that was marked off in like natural logs, the actual length of this curve is natural log of 2 root 3 units, which has a lot of other applications. We won't get to all of them in BC, but like clearly you can do this with like any shape you can create with different functions you can find the perimeter of. One way this is often used, which unfortunately we don't see in BC, is we can actually turn arc length into like surface area. So you can find like the surface area of pretty much any three-dimensional figure. We're just going to kind of stick and just be in arc length land though in BC. Any questions though for that problem? I just got one more for us to do. And Liam's going to stay awake for it, right?
Yeah.
Yeah. Okay.
He's so excited.
I know.
Set up this one for me. We are going to evaluate this one by hand as well. Going to go ahead and say like there's a lot of algebra involved in this one. There's a lot of algebra involved to actually evaluate this one by hand. This one you can't solve in terms of dy, so the function is I only want to do it in terms of dx. But there's no way to solve that for x equals. So set it up. If you want to try to start evaluating it, you can. Just know there's going to be a lot of like foiling and factoring kind of involved. But at least set it up for me first. So again, we're not going to overthink setting it up. The arc length is just going to be the integral of the square root of 1 plus the derivative squared. If I'm doing this in terms of dx, and the numbers on my integral sign are going to be x values, so I'm going to integrate this from 1 to 3. Y is that 1/8 8x squared minus the natural log of x. So what am I going to plug in? The derivative of it, which would be dy dx. Two ways you can do the derivative. You could distribute that 1/8 across first, or do it later because it is just a constant multiple. I kind of took the derivative first. The inside became 16x minus 1 over x, and then distributed it across. So what did I plug in? I can see that the derivative of that was 2x minus 1 over 8x. Now, if you were just asked to set this one up, then I guess one you would like a little bit better, but that would be your final answer. But I
Brown.
have to evaluate this one by hand, only because the algebra involved shows up enough, but it's also something I don't think most students just like pick up on their own. Not that you can't do it, but it is just kind of like, I honestly think you have to see it first to kind of see how it works out. So let's like talk about the algebra we know that will be necessary. There's nothing outside of the square root, so like there's not going to be like a u prime to cancel. So the idea when you're doing a problem like this is you want to simplify the inside as far as it can go before you find the antiderivative. So I'm just going to go ahead and just work with what's inside the square root sign. So I'm going to kind of come out of the integral for a second. So I have this 1 plus, and I have this 2x minus 1 over 8x times 2x minus 1 over 8x. And it's some messy foiling, but we do just want to go ahead and kind of like expand that out, then combine some like terms. So I did have that 1 hanging out in front. And then I had first, outer and inner are the same, so we have 2 of them, and it's a 2x times a negative 1 over 8x. And then last will become a positive 1 over 8x times 1 over 8x is 64x squared in the denominator. So I FOILed it out, simplifying some things. So I have like 2 times 2, which is 4, and an 8. So that's just going to leave a 2 in the denominator. Also, those x's are going to cancel out. So I have this 1 plus 4x squared. All that middle term just became a negative 1/2. The last term is 1 over 64 x to the negative 2. Could have left it in the denominator. And then combining like terms, I have a 1 and a negative 1/2, which I know is just going to become positive 1/2 when I combine them. And I have back to that final red line. Now let's talk about what we're looking at. This final kind of simplified version that we have so far is still all under a square root sign. We still can't do u substitution because there's nothing outside that square root sign. So we still need to figure out a way to simplify that trinomial, with the idea being that we can hopefully get rid of that square root sign when we plug it back in. Any ideas of what you could do with that trinomial? What normally do you try to do when you see trinomials? Factor. So let's try factoring this one. And you're like, Mr. Brown, that does not look like the trinomials I'm used to factoring. Let's try it. We know trinomials factor as 2 binomials, right? So let's just kind of start off with how it could work out. Like 2 things that multiply together to give you 4x squared. And that'll be 2x and 2x. Let's just see if we can think about that last term. 2 things that would multiply together to give you 1 over 64 x to the negative 2. 1/8 x to the what? Negative first. And it would need to be positive. And if this is going to work, when I FOIL all that back together, so like first times first, definitely 4x squared. Last times last, definitely 1/64 of x to the negative 2. I want the inner and the last terms to be 1/2. You can kind of see 2x times that 1/8 x, so we have like 2x times 1/8 x to the negative first. what's happening to those x's? They cancel. 2 times 1/8 is 1/4. And then when you do the inside, you're also going to get 1/4. Well, what's 1/4 time plus 1/4? The 1/2. So how is this going to be factored? It's actually a perfect square trinomial, and it's literally 2x plus 1/8 x to the negative first power squared. So not how we typically factor, not how we're used to factoring, but we can factor it. So I'm going to go back up to this integral to kind of plug it in. This was the original problem that we had. It's the same thing as saying the integral from 1 to 3 of the square root of 2x plus 1/8 x to the negative first squared. Well, square rooting that, it's just going to go away. I'm going to put that x to the denominator, so it's going to be a natural log rule. There's your simplified integral. So it does become one that we can find pretty easily. I guess arguably pretty easily, but one that we can find fairly easily. Antiderivative is going to be x squared plus 1/8 natural log of the absolute value of x, plugging in the top minus plugging in the bottom. So plugging in the top, I'm going to have 9 minus 1/8 of the natural log of 3, minus plugging in the bottom will become 1. The natural log of 1 is 0, so that would be 0. So the length of that curve after all that algebra would be that number. Told you there was some fun algebra with that one. Questions on that problem though?
How did you simplify y equals 1/8? Because I don't understand what you did.
Where am I looking at?
At the beginning, 1/8, 6. Yeah,
This
that
is
one.
the derivative. I didn't simplify it.
Oh, okay. I was just. All right, thank you.
Yeah, that's just a derivative.
Is it minus 1/8?
Where am I looking at? Yeah, that should be a plus. Sorry. Any other questions on that one? So again, fun algebra you need to know how to do. I will say, well, you're not going to complain about this, but your test is on a Wednesday, which is a 40-minute period, so like I just can't fit one of those problems on it, unfortunately.
Dang it.
I know, you're really upset about that. Still need to know how to do a problem like that, because I'm sure I can find a way to make it show up again on another test.
No, that's so unfortunate.
Yeah.
So what I do want you to do, and I just X out of OneNote, let me open it back up, I guess. You can go ahead and start on homework 5. Sorry guys at home, let me reshare my screen.
Homework 7.
Homework 7. And the homework I want you to do, so if you're looking at homework 7, so remember I did make homework 6 optional. So again, you're just going back and doing it if you want to. On homework 7, it's not too many problems. Like it's 4 through 16 multiples of 4. So you have like 4, 8, 12, 16, 34. It's literally 5 questions. I want you to use your calculator for all of them, except for numbers 4 and 12. One of those is just like that last example we did, which is a lot of the gross algebra. But again, I want you to practice spoiling all that and kind of doing it. The other one's going to be like a trig one that I want you to evaluate by hand. But the other 3, I do want you to just use the calculator. I do have a hint on here as well, and you'll see it when you start working on the homework. Number 34 asks you to find the perimeter of a graph that ends up looking kind of like a weird diamond. I would recommend, since it's symmetrical, just find the length of one side of it and then multiplying by 4. But that's the homework I want you to do. That's going to be the last homework assignment you have other than the briefcase binder. Again, do want you to practice doing 4 and 12 completely by hand. All the other ones, please just use the calculator for. So y'all can go ahead and get started on that. Again, enjoy your long weekend. Tuesday will be a review day.